Okay, we can start now. Hi, I'm Jean, and I'm an academic, and this talk is about ideas I've been thinking about, what I've been thinking about in getting these ideas out into the real world, and also some missing pieces that I've discovered there. And in case you're a time traveler, I'll just start by getting us all onto the same page. Our lives now run on software. Soon we'll have smart homes, driverless cars, and even automatic dating. In case you haven't seen the Tinderbox app for automatically swiping right on Tinder, well, I don't know if you want to. But first, to get to this nice world where everything runs on software and is magical, we need to solve the problem of software security. Hackers can now control our electric skateboards, our rifles, and even our cars. And some of these bugs take years to get fixed, and some of them never get fixed. Before you give up hope, I'll say that there's some pretty cutting-edge stuff happening in academia that promises to solve all these problems. So there are people working on encrypted databases, being able to query over data that's encrypted, undo mechanisms for replaying programs to figure out where the vulnerabilities were, program analyses that can detect vulnerabilities even before running a program, and also provably secure software that has mathematical guarantees of not having certain vulnerabilities. Something that I found really surprising is that my impression of the state of the art in industry is it's still firewalls. So we build a moat around our software and make sure that nothing bad really gets in. And they're really fashionable, very small very small moats we have these days in the form of microcontainers. But still, essentially, we have moats at varying sizes. And so the big question is, how can we take advantage of these research ideas in practice? And something I would like to brainstorm with all of you about is how we can better do this. So I'll tell you in this talk what I've learned so far so that we can use that as a starting point. So first I'll talk about my own research and the kinds of ideas that we think about in academia. And then I'll talk about what I've learned trying to connect academics better to startups, venture capital, and companies. And then in doing all this, I realized there's this big other missing piece, which is incentives to get people to pay for security. And so I'll talk about how we can involve, how we should involve consumers and policymakers in all this. And the goal really is to connect researchers to everyone else so that we can all work together to solve these problems. And I'm not saying researchers are more important than everybody else. I just happen to be a researcher, so I want to be connected. And I have some secondary goals of this talk. So I hear that we are annoying, have terrible time management, have different goals, and usually don't have money. And so I'd like to convince you that we're creative, fun, and really great people, that we just have different ideas of time management, that we have different time scales for goals, and I'll get to that a little bit later. And if you give us some money, that fixes the problem of us not having any money. And so once we do that, everything will be great. Let's start by talking about what academics think about. And really, it's not all academics, really just me. And the warning is that I am a programming languages researcher. I look at security from that angle. There are people looking at security from systems angles, from theory angles, many other different perspectives. So I just represent the one perspective. But here's the problem that I've been going after, which is the issue of protecting sensitive data being hard. So here are the hottest, latest data breaches. You've probably seen many images like this. We're not even surprised anymore to hear about millions, hundreds of millions of records being leaked from reputable companies like eBay and Adobe. And from my perspective, the big problem is that it's really hard to reason about our programs, what they're doing and whether or not they have vulnerabilities, and it's even harder to do this at scale. And so what I've been noticing is that people have just been giving up. They say, okay, we'll just do some heuristics, and well, information isn't really secure, but that's just the way life goes. And so I think we can do better, and I have hope that we can. But before I talk about my ideas, let's think a little bit about why existing approaches aren't enough. So there are various sophisticated techniques for encrypting data, But the issue often isn't that people aren't protecting the data at all. It's that they're showing it under the wrong circumstances to the wrong people. And something we have left is this reactive approach where we find exploits and then develop patches, but this leaves system builders always a step behind. So the approach that I'd like to advocate is factoring out policy checks for security and privacy so that we can reduce the opportunity for leaks. So just like how memory managed languages have prevented all sorts of bugs, I want to be able to do this for security and privacy. So in this approach, the programmer specifies high-level policies about how sensitive data may be used. The rest of the program is what I call policy-agnostic, and the system manages the policies automatically, so the programmer doesn't have to worry about it anymore. So before I get more into the solution, let's take a look at how this really goes wrong in the real world. So here is an example from the website Airbnb. Most of you have probably heard of it. Many of you have probably used it. You can turn your apartment into a hotel, or you can go stay in someone's apartment as a hotel. And they have various policies to keep things private about the host so that you don't go and just stay at their apartment without them wanting it. And they also have various policies to protect themselves. So one thing they do is, so this is the inbox of my student Chelsea Voss. She discovered this example and was really excited and sent it to me. And so she booked something on Airbnb. The host messaged her and said, "Okay, please text me tomorrow to my phone number hidden." So it turns out that Airbnb doesn't like it when you go off of Airbnb. They don't want you texting outside of the site, so they actually go through and they scrub all of the phone numbers. And you can make the argument that they're really protecting hosts who don't know any better. They could just, be kidnapped or something. But also, it's protecting the site in some ways. But if you go through in most places, you can't actually see phone numbers that are being exchanged through messages. They clean that up. And they do an okay job of making sure that the information isn't being leaked in various different views. So this is an email that Chelsea received, and it's from her host, and it's the preview of the message, and it says, text me to my phone number hidden again. So Airbnb found the phone number in this email preview, and they protected it. And so where things got interesting was Chelsea looked in her message preview in her actual inbox, and the phone number was not redacted. It just said to my whatever the phone number was. This is the same message. If you've been looking, you can see it's the same timestamp, same person, etc. But there's one place where they missed a spot. And so in this case, it's not a big deal because it seems like the host was actually trying to share their phone number, and so Chelsea could text them. But in a lot of cases, companies miss spots where they're actually leaking information that matters to you. And the scary thing is that it's not surprising that they do it because programmers have to navigate what's called policy spaghetti in very technical terms to convince you that this is a real problem. I wasn't able to get my hands on the Airbnb code, but here is code from the Hot Crop conference management system. It's a state-of-the-art software for managing academic conferences. So submissions, reviews, paper acceptances, that kind of thing. And there are academics are very sensitive about these things. You can't know who reviewed your paper, you can't know who submitted the paper, and so it's a really big deal to make sure that these policies get enforced. And how they're getting enforced is in terms of these highlighted conditional checks that I'm writing or that I've highlighted across this code. And so these are just two files that I've taken screenshots of, but you can see like every other line in this one file is checking if the viewer is a reviewer, if they're an author, and if this other thing hasn't happened yet, we have to do one thing or another thing. And these are just two files, but I looked through a lot of the files. There were checks in at least 24 of the 82 files that I looked at. And to update a policy, to fix a bug, to create a new policy, the programmer has to do coordinated reasoning across all of these files and make sure that all the checks are right. And as you saw, any missing check could result in a leak of information. So the big issue here from my perspective as a programming languages person is that languages weren't made with these kinds of concerns in mind. And so now the programmer has to go and do it by hand, and this is really error prone. And so the solution that I've been working on is to allow programmers to attach these policies directly to the data and allow the language and runtime to manage these policies so the programmer doesn't have to. So to give you an idea of how the research took place, we had one paper in 2012 about the policy-agnostic programming model and the guarantees. We spent a year cleaning it up, improving the semantics of it based on something called multi-execution, which I'll explain in a little bit. And then we tried to build a conference management system based on it and realized there are many other problems to solve to make this practical in a research sense first. And so then we spent a long time extending this programming model to the database and getting it optimized and making it more feasible. And I'll talk more about that. And to give you an idea of how things look in our system, here are 3 screenshots of code from our web framework. And what's highlighted is the policy checks. As you can see, they're all in one place. The rest of the code can be what's called policy-agnostic, and the runtime is responsible for differentiating the behavior so the programmer doesn't have to worry about that. So I've been working on this language called Jeeves, which is a research prototype language for doing this kind of execution. And in Jeeves, you have sensitive values that can be the secret value or this other hidden value. So your sensitive value, this house-looking thing with the actual number and hidden is a sensitive value, and the programmer can say, like, this phone number is a sensitive value. If you can't see it, then here's an alternate other value. And then that's guarded by some policies represented by the roof of the house. And you can use this as any other program value. So here we have a program that has a variable x. We set x equal to 0. If our sensitive phone number or other phone number, If our sensitive phone number or other phone number is equal to 8675309, then we increment x by 1. Otherwise, we return x. And so now the runtime is responsible for propagating values and policies. And the runtime is responsible for solving what to show based on the viewer. And so let's say our phone number was actually equal to that, but it's secret. Then only the people who are allowed to see that can see the incremented value of x. And everybody else sees the original value of x. So in this example, this is what's called an indirect flow. So we're not ever revealing the phone number directly, but we incremented some value based on the phone number's value. And information can be leaked through that. So for instance, like if you count like how many people are at Starbucks right now and they say only one person, then you can sometimes figure that out. So what our language can do is prevent information from being leaked through these kinds of indirect flows as well as directly. And my slides have started advancing themselves. I don't think that's a great thing. But now we're going to do a deep dive to give you an idea of why academics are useful, because we get to think about this stuff in great detail. So I'm going to show you the semantic rules for outputting in this language. You don't have to understand this slide to understand the rest of the talk, but you can understand this slide if you want to. So
it's very secure.
Yeah. So this is what the schema for a statement evaluation rule looks like. So essentially, in programming languages, we define what are called semantics for languages. This is an operational semantics that we've defined. So it's essentially math rules that correspond to an interpreter for a language. And then once we have the semantics, we can prove properties about it. But also, you can just write a lot of math into your paper and it looks cool. So for statement evaluation, we start with an environment sigma, a statement x. Down arrow means we evaluate it. And then what we get out is a policy VP, an output context OC, and a result R. And so if you're coding, you can think of like this is the signature for the function that says evaluate a statement. And we also have expression evaluation, where you start with environment sigma and expression E. Down arrow is evaluate. This down arrow comes with a PC, which is the program counter, which is essentially the set of branches you've taken up to that point. And then you get a resulting environment sigma prime and a value V. And statements have side effects, so like printing is a side effect, that's a statement. Expressions are just basically like things you can do in math, like functional things. And so now we'll go over what it means to be print as a statement. So for print, you start with an environment sigma, you say print EOC, the output context expression, who you're printing to, and what you're trying to print is ER. And then what you get out is a set of policies that were used to determine what you printed. A result OC, who you're actually printing to. So in this case, you could print to a person who you don't actually know. It has to be resolved according to whoever's looking at it, if that makes sense. And then you get back a result. And so the rule for this first says, well, we evaluate the output context and the expression to print in the appropriate environments. Then we go through and we collect labels and policies. So policies are indexed by labels. That's how we keep track of them. And then we make one giant policy based on the relevant policies. And so that's this giant lambda function. And then we evaluate the policies applied to the output context. So we essentially say, who are we printing to? We evaluate all the policies in that context. And then we pick an assignment of all the labels such that we're printing to the right person and we're showing the right version of the values to the right person. Oh, yeah. So the house value that I showed for the phone number, that's called a faceted value. And defaceting means you pick one or the other to show based on who's looking at it. And so what's actually happening is once you have a faceted value, everything that is computed with that becomes faceted. And so like if you have like faceted 0 or 1 plus 2, the result is 2 or 3, which is a new faceted value. Yeah. So essentially the big takeaway from this slide is we've thought about everything in great detail, how to propagate these sensitive values in the policies, and we've also proven properties about what it means to show the values. And so once we did this, we said, cool, we know exactly how our system works. Now let's try to use it for real. And this was not great. So my advisor in 2012, during my PhD, was running a student research competition, which is like a very small conference. And why that's relevant is there are not very many submissions to it. So he said, well, let's build a conference management system for it. So we said, great. We'll handle submissions and notifications and revisions and all of that. And I didn't really think this would work because we had just finished building a research prototype and I said, yeah, I'm pretty sure we're gonna run out of memory. Probably bad things are gonna happen. But he sounded so confident and so happy about it that I said, okay, let's just do it. So also before this, I'd never really built a web app with any significant backend before. So doing it with a research prototype language was like super painful. And also this was back when it was in Scala. And so it's, I think, harder to build a Scala web app than a Python one. Anyway, so we put it up, and then the emails start coming in. So this one student starts emailing me and says, hi, Jean, I don't know what the problem is, but I cannot log into the submission system now. It keeps loading, but the page just doesn't show up. Is there any problem with the server? And it turns out, yeah, when we tested it ourselves, it was fine, but once something starts not loading for someone, they start refreshing. And especially if running out of memory is the problem, then we really, really run out of memory. Yeah, so this poor guy, he really suffered from submitting his submission early because every day I would get emails. So he would email me and say, hi, I hate to tell you this, but the server seems down again. And it got to the point where he was still the only one submitting, but we were having so much trouble. Well, no, I think there were like 5 submitters. I knew them all very personally by this point. And I emailed my advisor and I said, I just don't think it's prudent to continue. And he writes back and he says, prudence is for the meek. Let's do whatever it takes to get the system to stay up. Are you available to talk on the phone now? This was like 11 p.m. I was like, I don't think this is very prudent. But everybody else thought this was very funny. So people started leaving Post-its on my desk about prudence all the time. So I had this is my monitor. I had my first goal was to have fun, but then I came back from lunch one day and someone said, fun is for the meek. Yeah, in short, it was not very great to try to make a production system out of our research prototype, but we learned a lot, which was, first of all, we need a solution for running out of memory. Secondly, the bigger thing that really came out of this was that I had been thinking about the language as an isolated thing. It was like, well, you know, we have these really nice guarantees, you can't ever leak information, but then I started building this web framework, or this web application, and all of a sudden it was like, well, what about this database? Like all of my computations are actually happening in these database queries. And in the language, I had these nice guarantees, but pretty much as soon as I call out to my database, all of the guarantees get subverted. And so then we went back to the drawing board and actually spent like a year or two figuring out the story for what happens when your language needs to interface with a database that doesn't know about all the guarantees that your language has. But the good news was I learned that web programs are often short and simple, and so that's really good for, first of all, coming up with a story for optimizing web programs, but also you can do some things with the database that you couldn't do for longer programs, essentially. So now that we went back and did all these things, we have a policy-agnostic web framework that we came up with. And the biggest thing is that the policies are associated with the program still once, attached to the database schemas now. The framework is responsible for keeping track of the viewer. So that's a nice thing about a web program. It usually, the viewer doesn't change very much. And the framework is responsible for attaching policies and associating them with the right data in the database. The framework is responsible for propagating the policies between the application and the database, and also making sure that values are displayed according to the viewer and what other properties that the policies care about. And so now, after many, many years, we finally have a system where you can build web applications and make sure you have the same kinds of guarantees that you had before. And so to give you an idea of how long this took, because people are always saying academics are lazy and have terrible time management, I'd like to show you the timeline of everything that happened and tell you that we weren't just sitting there and managing time terribly. So I started grad school in fall of 2008. And then it took us a while to figure out what I should work on. So in spring of 2009, we started working on this idea for separating out constraints or policies, essentially, about data from the data itself. And the first application we looked at was data cleaning, because we thought, well, that seems to be something where you would want to do this. But then it turned out nobody cared. So we spent a year working on that before in spring of 2010, we were like, oh, people actually care about security. It's a similar it's a similar case where you have a lot of policies about some values that you want to do something to, so let's switch. But it took us a year to do that. And in between, I was also taking classes because I just started grad school, et cetera. Then it took us really 2 years until we figured out what the right programming model for security, how to formalize it, and how to get it to work. And so also, like, in the beginning, it's hard when you're like a young grad student because you have to take classes and do internships and find yourself and all that. But you know, it took us a good 4 years before we really had our first paper on this. And then we refined the semantics for a while because we learned some more things. Other people were working on the same things. Fall of 2013. Spring of 2012 was when we started trying to build the conference management system. So that was, very shortly after we published the paper. That was, normal time. But then it took us a couple more years before we realized that, or what problems we had to solve and how to solve the problems having to do with the database. So a lot of that time was building case studies, but also figuring out how do we formalize a language that interacts with a SQL database? How do we model the SQL database? So one big thing we wanted to do was have this sit on top of an existing SQL database while still having our crazy language semantics. And so that took a long time. And then it took a while because people in the research community were like, well, why would you want to do it this way? And we said, well, because we built a real system and we need to. But we had to say things in other words so that we could convince them. So basically between, it took good 7-8 years to get from we're doing something to this is the thing we have. And now we've de-risked a bunch of things and you can take this and try to do it in your company, but it'll probably still be too slow and you'll have to do some extra work. But yeah, so we were doing work this whole time. When you're doing things that are really uncertain, you're trying to say like, hey, let's come up with a totally new way of thinking about things, and we're gonna make it work. Things take time. And so in the grand, so at this point we proposed a new programming model and de-risked the problem for people in industry. So now you guys can take it and try to do something with it. And in the greater scheme of things, as an academic outreach point, I'd like to say that people often look at us and say, well, what have you produced in the last decade? But maybe the last decade isn't even the right time scale to look at things, because there's a really, really nice diagram that I took this from, which is the time it took from something to be invented to becoming $1 billion industry. And for the internet, this was multiple decades. And so some points here are that research takes time. Adoption into the mainstream takes even more time. And also, many features in modern programming languages were incubated in research decades ago. So if you trace back a lot of things in Swift and Python and all these languages, they came from languages research from decades ago that took decades to figure out how to make it fast, how to integrate it with other language features, et cetera. And so, yeah, be patient, but also work with us, because it might go faster. And so now this brings us to the next part of the talk, which is how can we use research results in the real world? And the first thing to think about are some barriers to industry adoption. So what's preventing ideas like this from being used in industry? Well, in large companies, managers need to fight the status quo. They have to argue why this new change is more better than the previous change, and sometimes in terms of financial arguments, which is always hard for risky projects. And also, programmers need to manage legacy code. And so you need a story of how you can go from having a code base of millions of lines of some other legacy language to this new thing that might be a lot better, but might not work with a legacy system. And so something that I've been thinking about lately is, what about the startup route? So startups are a little more blank slate. How can you have startups adopt these new technologies and then have that infiltrate into bigger companies? So Sam Altman, who runs Y Combinator, has this quote that he would like YC to fund dozens of security companies in the next couple of years. And there's similar sentiment among other investors that this is an area they want to put money into. But the fact of the matter is, security is no Tindog. So if we think about what the prototypical hot new Silicon Valley startup looks like, it's something like this Tinder for dogs, which allows you, which matches dog owners with other dog owners. It's not clear if it's for dog purposes or for human purposes, but it's a fun concept. It has a slick design. Everybody can understand it. Your toddler nephew can pick it up and use it, and you don't have to change anything about your life to use Tindog. But if we think of, oh, you do have to change your life? Yeah, you might have to get a dog. But if we think about what the startup that helps us secure our software might look like, it's totally different. The concept is probably going to be highly technical. Probably only experts can really verify that it's doing what it sets out to do. And probably it's going to cause us to do things differently than what we're already doing, because our software currently isn't very secure. And so something probably has to change. And so if we think about it, there are some really unique challenges for security startups. First of all, security is expensive. As of 2015, I think it was estimated to cost $70 billion among companies. And the concept is highly technical. It's probably like some encryption thing or some way of designing your system that the layperson won't just pick up and say, yeah, this is really the way to go. Also, there are no flashy demos, so showing the absence of a bug is often not as sexy as showing the presence of a feature. So you sit there and you're like, yep, it's been 2 days, I still have no attacks. And also, adoption requires client expertise and/or trust. There's a huge market for lemons, so for security products that aren't actually doing the things they're supposed to be doing. And finally, this is more a hard thing for why it's hard for security founders, but solving a technical problem is not the same as building a product. And many of the people who are solving these hard technical problems don't have experience building products. So Justin Somani, who's the chief security officer of SAP, says a major reason security products fail is because they're made by security people. And I think he means it in the nicest way, but essentially user experience is not the same as having really strong mathematical guarantees. And if you'll notice, this tweet and this t-shirt, which you really can't see that Justin's wearing, have this nice CF logo. And so that's a nice transition to this accelerator. Oh, yeah. That I started with a friend last summer to incubate security research ideas. So Cybersecurity Factory is, it was an 8-week accelerator. Now it's a 10-week accelerator because we're growing. And we give teams $20,000 in a convertible note, a network of experienced security entrepreneurs and security people in an industry, office space in Cambridge, and also legal support in the form of legal advice that they don't have to pay back unless they go on and raise a lot more money. And we had a fantastic group of mentors last year, Max Krohn, who founded OkCupid, and Keybase, Raj Shah from Palo Alto Networks, David Ting from Imprivata, and a bunch of other big names in security. We had 2 teams in our pilot program last summer, AccuCrypt and Oblivilock. They both have very high-level descriptions of what they do that have to do with the cloud and data. So AccuCrypt is in charge of outsourcing data securely to the cloud. I think they're actually now in stealth mode, and they don't tell it. I tried to ask them, like, well, what can I say about you guys? And they said, oh, we're in stealth mode now. So who knows what they're doing now? And Oblivilock, their original mission was to protect data and metadata in the cloud, and that's also pretty general, so they're probably still doing that. These were both teams of PhD students. So the first 2 guys were theoretical cryptography people, one from MIT and one from Moscow. So we had to sort out how to get him here from Moscow. That was kind of interesting. And the second team was 2 MIT PhD students who already collaborated a lot in their research. And we had a lot of fun going through the process with them and learning. So neither of the teams had incorporated before they were accepted into our program. And as far as we know, they're both still in existence. AccuCrypt is planning to raise a round in 2 months, and Oblivilock is doing something. They're even more stealthy. But yeah, the teams, basically we took them from incorporation to having a product that they were pitching to real customers and getting ready to raise money. And first of all, it was great for the teams in terms of their education. So Chris Fletcher, one of our participants, said, I thought it was hard to sell my research. It's much harder to sell something for actual money. There were many surprises that they learned that were educational for us, but I think is also educational for the community as a whole. So here's a very conceptual diagram of how teams spent the summer. So here's how teams thought they would spend their time. So they thought they would spend most of the time coding, as you imagine of like your boot camp, this is how I get my startup off the ground. But they actually spent most of their time talking to customers and working on pitches. And so my co-founder, Frank, made this diagram in the beginning, and I said, Frank, this is really, really conceptual. And there's a tweet that got tweeted back at me recently from an article I shared where someone said, evidence for that completely random statement may be true or not, but random numbers don't equal truth. And the author of the article actually wrote back and said, it's called rhetoric, bro, which I really liked. So yeah, it's called rhetoric, bro. Yeah, and the biggest lessons for the teams were that people really matter. And I guess as academics, we don't realize this. I think maybe most people don't realize this as much as it's really true. But the first thing is that networking can really drive innovation. And so these teams in the beginning, we said, okay, you should go to these networking events, you should meet with people. And they said, no, we have to work on our product. And by the end of the summer, they came back and said, oh my God, we really learned a lot from talking to these companies. We learned about real problems. We learned about how we should be pitching ourselves, and also how we should be focusing our solutions. And one of them said, even if I never make this into a product and stay in research forever, this is really educational for me. Another point is that, wait, why are these showing up at the same time? Okay. Another point is that a good product drives conversations. And so if you have a good story for what you're trying to show off, the conversations you have and the subsequent innovation is better. And they also, the biggest thing that one of the teams realized was that you can have the best, most mathematically secure product, but if you don't find the right target market, you're not going to have a company. And so that was something that was also really important. And so essentially, these are lessons that you guys might know already because you're in industry, but we learned a lot from trying to push these ideas out there. And something that we discovered that's really fun is that Del Monte Foods is unexpectedly hip. So we had an article about us in Fortune last summer, and then the CIO of Del Monte Foods got in touch with us and said, you know, you might think we're just a food company, but we're really interested in innovation. And they have a pretty lean tech shop, but they said, you know, we're really open to experimentation, so whatever strategies your teams come up with, talk to us. And so our teams actually one of our teams went and visited them, and it turns out, so how many of you guys have heard of OpenFlow? Yeah, so it's a very avant-garde, like software-defined networking way of, so you can essentially use software to define how your network works, which is not how most networks work. And it's also very cutting edge. Like, I didn't expect a food company to really be that out there, but it was really cool. They were using OpenFlow and doing all this experimental stuff. And I think they had like less than a dozen people maybe working on this. So that was really, really cool to see. And another interesting realization was that for them, security problems are not just about we leak data, like the FDA gets on their case if they really have a security breach because it involves food. But yeah, so we had a good summer, and it confirmed our various long-running goals, which are to continue running the program because we still think it's important to try to bridge the gap between academia and industry. We want to continue trying to commercialize academic security projects. We also want to create awareness among investors, clients, and the public because we realize that if companies keep getting evaluated the same way, we're not going to see the right kinds of security companies coming through. We also want more collaboration and partnership within this industry. So we have this industry partnership pilot that we're doing this summer where Akamai tells us which problems actually matter to them, and then we try to have our companies work on those. And then also we want to create a community of founders interested in solving these technical security problems because we learned a ton from collecting all these people who have had a lot of experience in the security industry. And we hope to be able to pass on that experience to as many teams as we can. And so this is all towards creating these companies and getting them funded. But a really big piece that came up was how do we motivate customers to pay for security? So our companies started going out there and meeting with potential customers, and they said, well, it turns out a lot fewer people actually care to pay for this than we thought. And so so I actually had a lot of trouble finding an estimate for how much insecurity costs. So I found this one, which is kind of inflated, but I'll read it anyway to give us a sense of gravitas. So Jeff Kosev, who's a cybersecurity law professor, writes, a report released this month by the Atlantic Council and Zurich Insurance Group estimated that by 2030, an insecure internet would reduce global economic net benefit by 90 trillion. In contrast, a completely secure internet would result in a global net gain of 190 trillion. So some of these things are very abstract to me, like completely secure internet and 190 trillion, but essentially the takeaway is that it's very expensive to have insecure software. And the hard thing is that it's kind of a prisoner's dilemma, the security problem. So how many of you have heard of the prisoner's dilemma? Right, so it's this example in game theory where you have these two prisoners, they can either cooperate or they can betray each other. And if they cooperate, they actually get the lowest sentence, but the cost of one of them betraying the other is so high that the theoretically optimal solution is actually for both of them to betray each other. And security is kind of like that too, because it requires a lot of money, more employee training, more programmer effort, and doesn't currently provide any competitive advantage. So any individual company is not going to have a ton of incentive to invest a lot in security unless they do it out of principles or something like that. And some examples of how we need to care more are Snapchat, which, well, if you're, so hopefully you guys have heard of it. I don't know, I've been told that I'm the only non-teenager who uses it. But I mean, it has numerous privacy violations. I've actually ethically boycotted it a bunch of times. So then I'm like, wait, but no one is sending me fun pictures anymore. So I've gone back on. And it's also valued at $16 billion with 100 million users. And so no one is really punishing them for the security things they're doing. And the worst thing that's happened to them is like a light slap on the wrist from the FTC. But really, people are saying, you know, we can't live without this, even though they're leaking our information left and right. And also, there's something that we discovered in the summer was that there's not very much, people aren't getting audited as much as we thought they were. So one of our teams came up with their solution and they said, oh, well, anyone who is subject to HIPAA regulations should be interested in something like this. So they went out and they talked to hospital CIOs, they talked to dentists, and they found out that a lot of people said, oh yeah, we observe HIPAA regulations, and we also email x-rays around. And so first of all, there was this lack of knowledge of what it meant to adhere to HIPAA, but also a lot of people said, well, the HHS just doesn't audit us, so why should we spend any money trying to make sure that we adhere to regulations? And so, yeah, so even if there is policy, sometimes auditing doesn't happen, and things are still insecure. So it seems like from all of this, the most important thing is legislative change, but also like consumers and pushing people to audit are parts of the solution. Here's a quote from Joichi Ito saying, intentionally or unintentionally, poorly crafted or outdated laws and technical standards threaten to undermine security, privacy, and the viability of our most promising new technologies and networks. So yeah, so like our software, or like our programming languages, our laws are also often from the 70s. We need to update those. But even once we update those, as technologists, we need to think about how do we enforce them? And also, how do we create the situation where people aren't just embracing companies that have really blatant security violations? And so I tried to think for a long time, but I couldn't come up with great solutions. So I left this as an exercise to all of you. What should we do? Yeah, so I'll start wrapping up here. In conclusion, there are many pieces to securing software. We think about some things in academia, and the first step is to better connect academic researchers with industry. But also, we really need to change incentives for security if we're going to get anywhere. And once we get our ideas out there, we can iterate, but there are many things we have to do before we can be at that point. And so, yeah, I really think that if we work together, we can create the right ecosystem to secure our software. And I'm really excited to see what ideas you all come up with, because I clearly couldn't come up with anything. But yeah, I think we're at a really exciting point right now, because we have a lot of technology that's a good candidate for securing our software. This is clearly an important problem. And once we solve it, we can do a lot of really cool things. But now we just need to get from here to there. So yeah, thanks. I'll take questions now. Oh, and we're passing around a mic.
The policy-agnostic programming language that you're working on, is that something that needs to be at the language level, or is that something that could be in a library that's available in multiple existing languages?
Yeah, so that's a really good question. We call it a language because in research terms, it's a language in that we've defined the semantics for it and we've proven guarantees about it. But every time we've implemented it, it's actually been as a library. So the first time we've implemented it, it was as an embedded DSL in Scala. That was a library where if you used it, it behaved according to our semantics. And then we implemented it in Python, where we did dynamic source rewriting to get it to adhere to our semantics. And then also our web framework is just, it's like a Django-like library where we essentially monkey patch Django to get it to do what we want it to do. And so yeah, I think that our contribution from the research side is we define this is what you have to do if you want to get these guarantees, but there are many ways to do it without using a new language. And in fact, right now I'm looking at how can we eventually repair legacy code to get this kind of behavior and this kind of guarantees without having to write new code. And so once you have this is where we're trying to go. There's a lot of ways you could do it without having to adopt completely new stuff.
Hi. First, I just want to say it was a really impressive talk, and I really appreciate the time you took to put it together, so thanks. My question was like, so how do you sort of tie the pieces together, right? Like, because there's other components to, I guess like building a secure web app, like for example, the operating system or like other layers that, like a language or a framework have to run on top of, or that a database has to run on top of too. And I guess like, during the research, did you have any thoughts as to like how all those things would tie together to help build a secure system?
Yeah, so that's a really good question. And in fact, we made a lot of assumptions that you're running on top of things that are secure, that there are like these ways that you can't look inside your language runtime and all this stuff, but essentially you need a way to enforce those assumptions in the real world. Fortunately, there are lots of other people working on provably secure platforms for running things on top of, or ways of running things inside containers, essentially, where you can get security in your foundation layers. But yeah, there are other people working on how to enforce the assumptions that we made in our research, essentially. And so yeah, there are many pieces to the problem, and there are many people working on it. And again, I think it would be nice if we did it in a more coordinated way, but I'm not sure how to get there.
Thank you. Thanks for the talk. When it comes to changing legal policies, that's one thing, but it made me think, what about changing policies in the data over time? Like something's secure and we don't care about it now, but whoops, we changed our mind, and how do you enforce that later on?
Yeah, so that's a really hard problem. And in fact, so I think so are you asking about technical solutions to that, or like should there be social ways of enforcing that? Because so whenever I've talked to companies, changing privacy policies is something that's a huge headache, because first of all, how do you even figure out that this data was part of this other policy that from a long time ago? And then secondly, how do you enforce it? And so I think that one thing that I've been working on is, well, if we can associate policies directly with data and have better ways of doing that, then at least we can do better bookkeeping of this kind of thing. And there's also research in data provenance. So like in your database, keeping metadata with the data about where it came from and other things about it that can address that question. But yeah, I think that previously we thought of data as this very static thing, like we write it to our database and it's the same forever. But now, like the fact that we can go back and look at our data from before requires us to have like a lot more information, and that data is a much more active thing now. So I really think that we need new ways of thinking about the things we can do with our data and tying that better with the data itself, if that makes sense.
What advice do you have for developers who are coding every day to, incorporate security into their considerations for how they write code?
Yeah, so I think one thing is, so I don't write a lot of code in industry itself. So I'll say things that based on what I've heard from other people. But I think one thing I've heard is that people often design or they don't design security in the beginning. They design it or they put it ad hoc in the system later, and that's much harder. So I think thinking about security concerns in the beginning and thinking about how you can factor that out of your program as much as possible, even using existing programming models, will really help you down the road. Because if you wrote your security checks as just checks in your program versus as calls to some library, like already that makes a huge difference if you want to change your policy. And so that's just for like privacy type policies, but then there's other things like, you make sure that things are sanitized, or you make sure that like you're calling like encryption functions or something like that. And so like if you also like think about good abstraction for that, like I'm gonna do a routine to my data after I get it from the outside, or I'm gonna do a routine to my data before I put it back in the outside world, then like when things are updated and you figure out like this encryption scheme actually isn't what I wanted, you can just update your one function that does that everywhere instead of having to do it across your code. Because I think a big problem is this fact that you have this spaghetti of policies, and so like the more you think about factoring that out in the beginning, the more I think it's going to pay off in the long run.
There's a talk tomorrow on a Rust, which is a systems programming language with a new type system, and it's supposed to do a lot more static analysis at compile time and prevent some of the unsafety that we've lived with for a long time. Have you heard of it? Do you know anything of it? What do you think of it?
Yeah, I think languages like Rust and Go are great. Well, I think any language that essentially raises the level of abstraction and makes it so that you're not prone to unnecessary errors, I think is a great thing. And so for Rust, I think I particularly like Rust because, well, I've heard really good things about specifics of Rust, but also I think a lot of people will say things like, well, we don't want to use like Java or a memory managed language because we need control of our memory. And so systems level languages that give you nice guarantees take away that excuse, and they say, well, we're fixing some things for you, but you still have a lot of control. So I think it's really nice, and I think they've done a really good job.
So kind of as a follow-up question there, Rust kind of pushed memory management into something that could be statically analyzed by the compiler. I noticed that your implementation was a runtime check. I'm wondering if there's any research into something like ownership policies that is statically analyzed as opposed to a runtime.
Yeah, so there's a lot of work on static analysis for information flow policies, and in general there's various approaches for static analysis for security. For the kinds of policies I'm looking at, the one reason that a lot of us look at runtime versions of it is the static analyses require programmers to annotate the programs in certain ways, like this is the policy, this is how it propagates to the program, and that can be kind of cumbersome. But I think ideally you should be able to statically analyze your program because that cuts down on the runtime overhead. But there's this trade-off between, like, sometimes if you want your program to be statically analyzable, you have to put in all this upfront work, whereas you can just let it run and things get caught. But then there's the runtime overhead.
Right, so it's kind of the same trade-off with Rust.
Yeah.
Where now you have to reason about lifetimes, but the compiler can catch your errors.
Right. And so yeah, in all of these things, there's the static runtime trade-off.
Thank you.
Yeah, thanks.
Hi, thanks for the talk. I'm just wondering if the policy framework that you came up with accounted for sort of row-level permissions at all. Like there are a lot of dynamic ACLs where you're really permissioning down to the unique row level across like thousands or millions of different roles.
Yeah. So essentially, we let you have permissions at the field level, but if you did it that way, it's much slower than if you did it at a coarser level of abstraction. But essentially, like in our database schema, for every field, you can say like these are the permissions on this specific field. And so you could encode row level permissions that way too.